Hello everyone, welcome to our presentation on Stock Market Sentiment Analyzer, a project developed as part of the course Deep Neural Networks for Natural Language Processing. We are Group 3 and today we'll be walking you through how we built an intelligent system that analyzes and interprets market sentiment using deep learning techniques. Before we begin, let's meet the team behind this project. We have Ananya, Sneha, Aditya, Twissa, Hari and Tanmay. Here's a quick overview of our presentation. We will start with a brief introduction to our project, followed by data fetching and pre-processing. Next, we will explain our ranking and similarity-based filtering, followed by data generation and model fine-tuning. We have key phrase extraction and visualizations as well. And finally, we will wrap up with a live demo of our project. Now I'll pass the time to Aditya.
News moves markets, but which news and by how much? That's the uncertainty our project eliminates. Traditional investors manually track headlines, trying to gauge market impact. Our AI-powered system automates this process, analyzing sentiment at scale to identify whether stories are bullish or bearish. We are turning qualitative news into quantitative signals, giving investors the clarity they need to act with confidence in volatile markets. Let's now look at the complete system architecture and understand how all the components work together to deliver intelligent market sentiment insights. Starting at the top, our data collection module fetches real-time news articles from the FinHub API and immediately deduplicates them to ensure we are working with unique content. This gives us clean foundation of fresh market news. The data then flows into our data processing stage where we clean and normalize the text, removing noise and standardizing financial terminology. This ensures consistency across all downstream analysis. Once pre-processed, we move to rule-based ranking. Here, three scoring mechanisms work in parallel. The recency score prioritizes breaking news, the event magnitude score weighs the importance of events like earnings or partnerships, and the company relevancy score filters for target companies. These combined scores produce a ranked list of most impactful articles. Next, the similarity expansion module computes cosine similarity between articles, clusters related stories together, and expands a top-ranked article to include the full context around each major event. We then select the top-end articles for deeper analysis. At the core of our system is a sentiment analysis engine, powered by the FLAN T5 model. This classifies whether each article is bullish or bearish for the stock market, providing context-aware insights into market direction and investor sentiment. Running in parallel, our key phrase analysis module extracts and classifies financial entities like companies, products, and executives, identifies the key topics and players driving market movement. Finally, the result output phase visualizes the entire analysis pipeline and delivers the final output, a ranked list of articles ordered by importance, extracted key phrases showing what's driving the market, and clear bullish or bearish signal for each story. This comprehensive view enables traders and analysts to quickly understand market sentiment and make informed decisions. In the following slides, we'll explore each of these components in depth, the algorithms, the technical implementation details, and design decisions that make the system both accurate, actionable for real-world trading scenario.
Hi, in this section we will go through the data fetching and pre-processing. I am Twissa and I will take you through the data fetching module. We have used Fast API to build our server where whenever a call comes to /API/fetch and rank, we first check whether the data is present in cache or not. If it's a cache hit, then we return the results that are stored in our cache manager. Otherwise, we make an API call to FinHub with a specified company name that has been selected by the user and the specified timeline which has been set to a month for this project. The articles written by FinHub may essentially contain some similar articles that have been paraphrased. This is because FinHub gets its articles from various sources. Therefore, there is a need to apply semantic deduplication. To achieve this, we have used the capabilities of NLP and we have combined the news headlines and summaries and created embeddings out of these. Once we have these embeddings, we have used agglomerative clustering to cluster the similar articles based on their cosine similarities. Then we have taken representatives of each cluster to get the unique news articles. These unique news articles are then passed on for data pre-processing. The final results are stored in our cache manager and the pre-processed data is returned. The key features of the backend system are intelligent caching, which reduces the API calls by 95% and leads to high performance. The data is retrieved in sub-milliseconds. Semantic deduplication reduces noise by 85% and also preserves unique articles. Configurable max articles parameter allows for dynamic scaling and you can adjust this value based on your processing requirements. Apart from semantic deduplication, we also have another layer of deduplication, which is done on the basis of the IDs of news articles that are returned from FinHub. We also have scalable API integration. FinHub API actually has certain limits with respect to how many calls can be made in a minute. Along with that, the number of articles that can be returned within one API call. So to respect these limitations, we have utilized async calls along with pagination and exponential backoffs. Therefore, if you want to extend the timeline or make certain other changes, the API still remains scalable and can be used as is. Lastly, we have real-time performance monitoring, which means we have detailed log to track latency and analyze the number of cache hits or miss rate along with the other performance metrics. Now I will pass on to Sneha for explaining the data pre-processing pipeline.
I will be going over text pre-processing, where a financial aware data cleaner is employed. So the input to this particular function is in the form of a JSON string, which is returned by the API call, and the output is a clean JSON string. First, standard cleaning methodologies are applied, where unnecessary information such as URLs, hashtags, emails are removed. The text is normalized by converting it into lowercase, and it is also stemmed. Then, certain specific methodologies are applied to make this particular process financial aware. So first, there is financial text protector, which preserves important information such as currency, ratios, financial acronyms, percentages, and it does this by employing the RE package in Python, where the pattern of that particular text is found out and preserved. So this will help in retaining the context for further sentiment analysis and prediction. Then, special stop word removal is employed. Normally, stop words might remove words such as S&P or IPO, which don't really seem to contribute much to the meaning of that particular text. But in our case, it does contribute to the meaning of the text, and these are specifically preserved. So here is an example of what the input and the output to this function look like. So the input is in the JSON format, and the text here is in all caps. We see a lot of punctuations, a lot of numbers, a lot of stop words. The output is also in the JSON format, but all the text is now in lowercase, and there have been stop words that have been removed, for example, the word off. But all the numerical information, percentages, and all of the years, important information like CEO Elon Musk, these are retained. Now over to Ananya, who will be talking about ranking and similarity-based filtering.
Thank you, Sneha. Now I'll be talking about the rule-based ranking. So the purpose of this rule-based ranking is to intelligently prioritize financial news articles using a multi-factor scoring approach that combines the following. First, we have the recency score. In financial markets, timing is everything. News from yesterday is far more valuable than news from last week. Therefore, we use this exponentially decaying model. Here, T is the number of days since publication. And this decay is smooth and continuous, ensuring recent news is always prioritized. Second, we calculate the event magnitude. Since not all the news is equally important, we've created a 3-tier keyword classification system based on financial impact. So high impact events like earnings reports, mergers, CEO changes have a score of 80 to 95%. Medium impact events like partnerships and product launches have a score of 45 to 60%, whereas low impact events like general commentary and opinions have 20 to 30% of importance. This ensures that market moving events are ranked higher than routine updates. Third, we have the company relevance score. When analyzing sentiment for a specific company, we want articles that are actually about that company, not just generic financial news. This component acts as a dynamic multiplier. If an article mentions our target company 3 or more times or is moderately relevant, it gets boosted. And if it is context dependent, that means if it is mentioned only once but also talks about its competitors, it will get a reduced multiplier of about 0.6 to 1. However, if it goes off topic, it will be penalized. Finally, we combine these 3 scores using this weighted formula. We weigh the magnitude higher than recency because impactful events matter more than just being recent. The company relevance acts as a multiplier to amplify or suppress the base score. Now, what makes a ranking system truly intelligent is the integration of named entity recognition. We use Spacey's NER model to extract organizations, products, and persons from every article. This entity extraction is crucial because it transforms our rule-based system from simple keyword matching into context-aware scoring. This NER integration powers 3 key capabilities: entity-aware contextual scoring, which prevents false positives; smart event prioritization that ranks only genuine and newsworthy events; and company-focused relevance filtering This detects competitors and applies dynamic multipliers to ensure we're analyzing the right company. Finally, we have configurable weights, a flexible framework with tunable recency magnitude balance and adjustable decay rates for different use cases. So from this input, our output will give the corresponding scores and will rank the articles accordingly. These top ranked articles will then move forward to the next stage of our pipeline, which Tanmay will be talking about.
I'm Tanmay, and I worked on the similarity-based filtering for this project. Our core methodology involves a 4-stage pipeline, the first of which is article stratification. In this stage, we select the top 5 articles out of the entire list that is returned to us from the previous steps. Next, we do an LLM summarization. We use the Grok API to carry out inferencing on the top 5 articles. The API generates a summary based on the top 5 articles and then proceeds with the next steps. Stage 3 involves a neural encoding. Sentence BERT is used to encode the summary, and then this is used to calculate a similarity score with the remaining articles. The similarity score used is a cosine similarity. The main feature of this is precision and recall. We use top K selection, which means that we can select the number of articles that we want to filter out to send to the downstream applications. This is configurable and is just a random selection. Also, we have a similarity threshold. So any articles that are above this similarity threshold are also appended and returned to the downstream tasks. The main decisions that we took as part of this pipeline are as follows. We used LLM summarization instead of normal natural language processing, as an LLM is faster and better captures the context and the semantic coherence of all the articles. Sentence and BERT encoding was used instead of word2vec or other embeddings because it is able to produce semantically meaningful embeddings which help in the similarity comparison in the future tasks. Again, a dual threshold strategy was used. So user can configure a top K as well as a similarity threshold in order to keep the number of articles to whatever filter they want. And last but not the least, field preservation makes sure that all the information that is there in the data returned to this step is also passed downstream. This helps maintain all information for future data analysis, such as rank score, relevancy score, company weights, etc. Future extensibility for this step could include extractive versus abstractive summarization strategies, adaptive threshold based on what the score distribution is like, and even multimodal expansion with stock data and proper social media data. Thank you.
Hi, I'm Srihari and I'm going to be talking about data generation and model fine-tuning. For the synthetic data generation, upon setting up of the required APIs, a prompt is constructed requiring structured outputs. Once these structured outputs are cleaned, they are formatted into a CSV file with the source name, source, sentiment, and a reason. The FLAN T5 base model was fine-tuned and tasked with sentiment and reasoning generation. The input for which is a news article and the output is a sentiment varying between good, bad, and neutral and its corresponding explanation. The model achieved a 95.85% accuracy on the test set. The model was trained on 4,980 financial news articles with a 70-30 split, which is about 3,486 samples for training and 1,494 samples for testing. The model ran on 4 epochs with a learning rate of 0.003. For tokenization, the inputs were set to 512 tokens to capture full articles and outputs to 128 tokens for sentiment and reasoning. This slide also shows us what the data in the CSV file looks like. In this slide, we can infer how the predicted output, which is the sentiment reason given by the model, matches the true output of sentiment and reason for a given input news article. This shows how well the model performs.
The key phrase analyzer works through a clear sequence of steps to identify meaningful concepts and the sentiment from text. To start by breaking down the text into sentences and words using NLTKs, tokenizers, and POS taggers. Stop words are filtered out and words are normalized through lemmatization. The system then runs multiple extraction strategies simultaneously to capture different types of signals. Noun phrase chunking and POS-driven patterns pull out descriptive phrases and compound nouns. Named entity recognition spots organizations, products, and executives through capitalization patterns. Domain-aware patterns identify technical terms, acronyms, hyphenated expression, release quarters, and chip or platform-related compounds. The analyzer also looks for collocation and n-grams to highlight frequently co-occurring word pairs and contextual phrases. Each phrase gets a sentiment score based on pattern matching lexicon count specifically tuned for financial and business language. Multi-word patterns like record earnings or execution risk carry strong signals. The system checks words in both their original and lemmatized forms against positive, negative, and neutral indicator lists, then converts these counts into confidence scores. Multi-word patterns naturally receive higher confidence. The system filters candidates by length and stop word content, removes duplicates, and ranks them by sentiment confidence and phrase length. The final output organizes the top positive, neutral, and negative key phrases along with metadata about extraction methods and counts. This multi strategy approach strikes a balance between precision and resilience when analyzing real world financial text. In the interface, each article appears as an AI enriched card showing overall sentiment badge, a highlighted reason, top key phrases with confidence scores across sentiment categories, and a compact summary of counts and extraction methods. The card includes quick filtering and copy export options so you can inspect the most relevant signals right away. Users can also download the entire data in JSON format for further analysis or integration with other tools.
This is the demo for SentiStock, our NLP project that performs financial analysis using AI. We start with giving users a choice for different companies to perform the analysis on. These are all companies related to tech and AI and are leaders in those fields. Let us select NVIDIA, for example, and click on Analyze. Once we click on Analyze, this will be doing a bunch of things in our backend as shown in the PPT. It will fetch the latest news articles from the FinHub API. It will rank them based on recency, relevancy, and then it will also perform a similarity-based filtering to filter out only the most relevant articles above a certain threshold and top K value. This will be then passed to a fine-tuned FLAN T5 model that performs sentiment analysis on these articles to see if they're positive, negative, or neutral. And then it also goes on to do a key phrase extraction that also is displayed in the articles. As you can see, the analysis is complete. We can go more in depth in each step. Step 1 was all about fetching and ranking the articles. There were 250 articles input from the API, but we only selected 19 based on our top K and similarity threshold values. You can see the AI-generated summary that Grok has generated based on the top 5 articles by rank score. These are then passed through a similarity check with the remaining articles. And these are the 14 articles out of the top 250 that are chosen. Then our pipeline performs a sentiment analysis on our fine-tuned FLAN T5 model. This segregates it into positive, negative, or neutral, and then it also extracts some key phrases. You can also see that the key phrase has intelligence to bullish signals, bearish signals, or neutral themes based on stock data. And you can see that these articles are displayed in these cards with the AI sentiment analysis, the key phrases, what their rank score was, and when this happened. We are also able to filter these based on positive, negative, or neutral, and we can also sort them based on their lowest rank, highest rank, or even their most recent articles. Thank you.